right now. I feel like you wouldn't like it.
Me?
Oh yeah, I know. I was like looking at this and so do I. Like, yeah, my bad. You're disrespecting my bad again. My bad. My bad.
Right. So these timer 246 are different timers. The timer number with the even numbers are different from the 156. Like timer 0 is different as well. 1, 3, 5 runs a different way to overflow. Remember that. What's timer 0 overflow flag? Oh yeah, but it's in the register. The register's name is what? That's why it's different, you know. So for timer 0, it was int count, 0 bits. Dot TMR0 IF, right? But for these ones, timer 135 with even numbers, with odd numbers, are PIR bits. Dot timer X IF, right?
Yeah.
For these ones, the register's name, I have to look at it, but it's the way that works is it's not overflowing, then turn on the flag. It's comparing with the register. It's called period register. PRx. That could be confusing. So I have to work with timer 0, I have to work with timer 1, 3, but now we are dealing with 246 for PWM. It's helping with PWM. It's always paired with the PWM modules. And the way it works is to compare. So the timer module itself has a register called period register, PR. Depending on the number, it's going to be PR2, PR4, PR6. And it's the same way to count. It's counting from 0 to whatever. And whenever it matches this number, it turns on the flag. So the flag must be timer X IF as well, but in which register I have to look it up. Don't want to make it up over here. It could be PIR bits as well, maybe. But it's just within the register, okay? That's how that works. So during the PWM setting, you have done that in the in-lab. You chose timer 2, remember? You couldn't remember? Let's go there and take a look. PWM settings. Not here. Not here as well. Right? You pick up timer 2. So which means the PWM period will be defined by timer 2. You don't need to know how the internal hardware works, because that was done by people who wrote the Verilog and tested on IPG and eventually taped it out as a chip, tape out. Which means you design the IC and fabricate it, okay? So the hardware, I don't think, so embedded system level is just C level. C level. We don't touch the digital blocks inside. So we don't need to know. That sometimes we feel it's painful because we don't know what's going on. We just need to remember it. At this moment, if you just look at this example, it's just telling you, timer 2 is paired with PWM module 1. Why is module 1? Because ECCP1. You just have to trust it. It's going to be paired with PWM module 1. All right? How do you do it? It's just in MCC, drop down menu, pick it up. Right? There's a register associated with it. After you set it up in MCC, it's gonna read that number to that register. Okay? But you don't have to remember it because MCC is over there. Just drop down menu, pick up timer 2. You could also pick up timer 246. So the even numbers are the timers used for PWM modules. So we have been using timer tool for all the PWM modules. So how that works, PR register will define, for example, here's a PWM, okay? PWM. From here to here will be the PRx count. So that's the 8-bit register. It's a byte storing the number that will make a timer to overflow or timer X.
Was it 8-bit?
Yeah, it's 8-bit. Yeah, that's pretty interesting, right? I'll talk about that later. I'll let you guys know. And if we use whatever Dr. Carlson's website and all the numbers, I did all the calculations, it matches. Don't want to confuse you too much. We'll talk about that later, okay? It didn't cause too many issues, just a little bit, tiny problem, but that can be solved by adding a 1 to that to turn all the LEDs. I'll just show you pretty quick. However, if you look at the data sheet and try to match whatever the theory being written on the data sheet to whatever posted on the website, it doesn't match. I've been looking through that for a few days. I was trying to find out why. Maybe you guys later, probably during the weekend, I'll figure it out. I'll let you know on Monday. But if you figure it out as well, we can talk about that during this lecture. Not sure if we can reach that far yet, but let's do whatever has been matching, whatever my calculation matches Dr. Carlson's website. Let's do that first. It doesn't affect your lab. So for lab 5, you follow instruction and the calculation and make a little bit change to the code. I'm going to tell you what change to make to the Dr. Carlson's code. And it should be able to turn off all the LEDs and tour the color. But you know, if you're going to match with the theory on the data sheet, it's a little bit, you know, something's wrong over there. We'll talk about that later. Let's go through the theory first. So remember that PRx, confusing, right? What you're talking about. We'll reach there later, okay? So now it's very simple. Let's just follow. So far, so good. Everything matches the theory, okay? PRx, the PR register, period register, 8-bit, okay? 8-bit. Timer 2 is counting, depending on the prescaler, 1 to 16 or 1 to whatever, okay? It just use that frequency to count that number. We have done that so many times. Easy, right? If you still don't know how to do that, if you are given with the count, how to calculate the time, given with the time, how to calculate the counts, still don't know how to do that, make sure you spend time during the weekend and early next week because it's going to be on the midterm exam. So here, easy, timer 2, prescaler given, and count to this to reach this 8-bit. Timer 2 is also 8-bit. It's an 8-bit timer. You cannot change it. Doesn't like 135 and 0. You can modify it in MCC, right? You can change it through 8-bit to 16 bits. But this is exactly 8-bit. So use an 8-bit timer to count through an 8-bit number. Is there any problem? No. Right? You can eventually reach that 8 bits, no problem at all. Okay? So this is called the duty cycle, the duty value. This is controlled by the CCPRx and the DCxB, DCxB, I'm sorry. DCxB register. So this is 2 bits. And this is 8 bits. Now here comes the problem I was talking about.
It's 10 bits.
Yeah? It's a big question mark. However, all the calculations on Dr. Carlson's website is always assuming everything here is 8 bits. It's not using these 2 bits at all. I don't know how that works with the hardware. I was looking at data sheet. They didn't talk about the details. It's not affecting our lab again. If we just assume everything here, we just use whatever here as an 8-bit number, it's going to work. But we can figure that out over the weekend. If I cannot figure that out, I'm going to ask Dr. Carlson, email him, or ask Dr. Sharma or someone else. So all the TAs couldn't remember the details already. It's just too deep in the theory. No one can still remember. And none of the tutorials talk about that. Okay. However, let's assume it's 8-bit. Okay. Everyone's happy. Easy. Let's do it. So we are based on that theory, and we are going to do all our calculations. And these could be on the exam as well. Okay, PWM period. Let's draw a table, prescaler. 1 to 1, 1 to 4, 1 to 16. It doesn't have other options like 1 to 2, but you may see 1 to 2 on the exam. It's okay, just theory, right? Just calculate it. Period. For timer 2, okay? Timer 2. How to calculate it? What's a period? So timer 2 is 8-bit, right? How many counts do you have in total?
2 to the 8.
2 to the 8 will be 0 to 255. How many counts? It's easier than 2 to the 16th, right?
Yeah.
So it's 0 to 255 will be 256 counts, right? So for 1 to 1, you got 256 counts. Finish that 256 counts with a 1 to 1 prescaler, enter that 60 megahertz clock. I've done this for millions of times, right? Easy. So counts is given. To find time, what to do? Divide it, right? Divide it by,
Divide by 4.
yeah. No problem here, right? Yeah, because you can flip after division. You can flip seconds to the top. So eventually you are getting a time. So what's the result here? Because 256 divided by 16 is still giving you 16, right? So it's basically 16 what? How long? Microseconds, right? 16 microseconds. So where is that 16 microseconds? Where is it? Here. So when you are trying to define a PWM, you are trying to send that PWM somewhere else, okay? So you need a two time parameters. What are they? The period and the duty value. If you are given with the period and the duty value, you can definitely define that PWM, right? Period and ratio. That's everything you need to know, right? Period and ratio. It could be here, here, here. So if you are given with these two values, you know exactly what kind of PWM you are giving to the output. Make sense? Okay. So this thing here, the PR register is a parameter to define this. Okay. If we put a so maximum period, the maximum period that the timer 2 can give you with the 1-to-1 prescaler, it's going to be 16 microseconds. Can you have a shorter period? Can you have like 10 microseconds? 10 microseconds period PWM. If you are using 1-to-1 prescaler, are you able to provide a 10 microseconds period of PWM waveform? Yes, because this is maximum. This is maximum. It just use less number of counts. How do you set a less number of counts? How? Yeah, time. So how this works? Timer 2. The timer 2 is the register, right? It's 8-bit. So it's able to count inside. We have done that so many times, right? There's another register called PR2. It's designed. It's a hardware, certain hardware designed in the timer 2 module. So it's actually comparing these two. Okay. There's no like timer 2 right. Is there a timer 2 right? You still could set up an initial value, but usually we don't do that because you can set up the value you want to reach in PR2. So there's no reason that you still want to do the timer 2 like right timer or something, right? Because you can set a value. For example, this is PR2. They are both 8 bits, same length, same width, okay, same width. So, for example, you set PR2 here, okay? So when timer 2 starts counting, whenever it reaches this point, it's going to turn on the flag. Done. So why do we still need to do the timer 2 right timer blah blah, right? Like 0x1 4 zeros minus something, right? We don't have to do that anymore, do we? It's not comparing to itself. It's comparing to PR2. Now, okay. And what about the second one? 1 to 4. What's the maximum period? Still 256 counts, right? This doesn't change. Still 8 bits. Divided by 16 mega. This frequency is divided by 4. So it's slowed down, right? So this is giving you 64 microseconds. For this one, still 256 counts. And divided by 16 megahertz per second divided by 16 times, which is giving you 256 microseconds. Now, here comes the example. Okay, there's a question on the exam. Question. Create a 100 microsecond period PWM prescaler. Which prescaler to use? Which prescaler we should pick up? And what counts in PRx for PR2? Let's say PR2. Okay. Which prescaler should we use? Definitely, you can pick up different ones, right? Oh, you cannot. Can you pick up different ones? Can you pick up this one? When overflows, still not reaching that yet, right? Overflows within 64 microseconds, still not reaching that yet. Okay? So you want to pick up this guy. So whenever it's reaching this time amount, it's still within that PR register value. So we should use 1 to 16 prescaler. So what's the count you want to use for that PR? What is given? What is given?
You got time.
You got time? Where's the time? Here. What else? Prescaler.
You have counts per second.
Clock. So how to do it? 100 microseconds divided by what? So you are getting a second, right? Because this count is counts per second, so it's perfectly getting cancelled. You're gonna use 60 mega per second divided by what? Slowed down by 16 times by the prescaler, right? That's how I'll do it. Micro, mega, cancelled. Seconds cancelled. Sixteen cancelled. Wait. What did I do wrong? Oh, seconds. This has to be cancelled as well because micro divided by this is a second, right? Okay. So what's the count? What's the count you need in PRx, PR or PR2? Let's say PR2. Do you have PR4? Is there PR4 in the microcontroller? Is there PR3? Is there PR2? Belongs to what? Timer 2. Is there PR4? Yes. Belongs to timer 4. Is there PR6? Yes. Timer 6. Why? Because the even numbers of timers are serving the PWMs. So is there PR3? No. Timer 3 doesn't have PR. Timer 3, so timer 1, 3, 5 are the ones using a different technology in there. Okay? So how many counts do you need? 100 counts. To put in where? Put in where first for the configuration? PR2. So when you are configure that or do all the setups at the very beginning, you need to put 100, convert to hex value, and place it in here, okay? In the initialize function at the very beginning. Clear on this, no problem. Good so far. If you don't look at the data sheet, it's good. Another question, how that works. So let's summarize here really quick by looking at this. Okay. So when timer 2 equals PR2, this is gonna happen. Could you let me know what are the following actions you want to take after this timer 2 reaches here? It's gonna do something, right? It's gonna do something to the hardware. So for timer 2, if we are using ECCP1, we are picking up pin RC2. How do I know that? Does it click in your mind at all? So RC2, right? RC2 is the first PWM module. So if you are using like CCP1, it's by hardware, it's connected to RC2. So the CCP1 pin is with RC2. That's how I know it. It's RC2, okay? However, you are pairing a timer 2 with ECCP2. I'm just repeating. How did I do that? Repeating, which is good, right? For learning. How did I pair timer 2 with PWM 1? Here, timer 2. I chose it. ECCP1 set up, right? PWM, I pick up timer 2. That's why when timer 2 matches PR2, I put in the register. It's going to do something to RC2. Make sense? That's how they are connected, interconnected. So now I want to let you guys tell me at RC2, after this one matches this one, what the digital logic inside is going to do to RC2. What's going to happen? RC2 is a pin, it's a metal pin. What's happening?
Pushes to high.
Yeah. See? Goes high. So whenever timer 2 equals this one, first thing to happen, RC2 is 1, right? Give a 1 to RC2. What else? So RC2 is also CCP2, right? CCP1, sorry. See? Easy to get confused. So CCP1, which is RC2, put a 1 to it. Why you want to do that? Because that's how you create the PWM. You want to set a high, right? Okay? So it will stay high. Then it's going to start counting until when? Until that reaches what?
Your duty value?
Yeah, the duty value. Let's still assume it's an 8-bit value, okay? Assume it's an 8-bit value. CCPR, that's a register, right? It's like CCPRx, L and H. So L is holding that 8-bit value. Whenever it reaches, when timer 2 reaches here, what's happening is this value is being latched into CCPRxH. You don't have to ask like why this is designed that way. Probably trying to avoid any of the. I think I saw that on the datasheet, like glitches or something. So it's not. But that doesn't make sense because I cannot see the details of the transistor level circuits. So they tell you it's gonna send it to this byte. They just assume it's gonna be sent to this byte. Oh no, actually. So whenever this one reaches, this one is sent to this byte over here. That doesn't matter. It's still not affecting your design anyway. So after this one is set high, it's going to start counting for that duty value. It's going to start for counting that one. So timer 2. Oh, another thing I have to do here. Timer 2. You have to give a 0 to timer 2. That makes sense, right?
Reset it?
Yeah, here. Because I have to recount it. Start from 0. Then it reaches PR2 again. We'll set this one, right? So I have to start counting from 0 because every time it's trying to match with this value. That's another action you have to take. That makes sense. Let me show you. I draw this again, okay? So from here, timer 2 It's gonna count from starting from 0, okay? All right? Why? Because it's getting reset from the previous one. Whenever it reaches PR2, it's getting reset. That's why timer 2 becomes 0. Okay? Now let's just restart. Reset everything. Restart from 0. Okay? Starts counting. Reaches this point. So what's the count here? CCP. Yeah, the duty value. CCPRx L or H. Doesn't matter. It's the same thing. It's getting duplicated to that register. Just one byte. Okay? Then do what? At this moment, do what? No.
You push down the push.
Yeah, CCP1 or what?
C2, RC2
What?
equals 0.
Okay? You do it, then you pull it down. So you can define that duty cycle by doing that. You have to pull it down. Otherwise, it's always on. You don't have a certain duty value, right? So you have to pull it down. Then what's going to happen? Do you want to set? Do you want to reset timer 2 as well?
No.
Why?
It needs to count.
It keeps counting to where? Yeah.
So how would you like say that it's like if the timer gets to the count CCPR, what is that? CCPRx 4H?
No, it's L.
The low
It's
slash
low.
high?
Yeah, that's right.
So whenever the timer gets to that count, held in that number, then you push low? Okay.
And then you reach here, right? Timer 2 becomes 0. RC2 or CCP1, right? Becomes what? 1. So turn it on. Just keep doing all the cycles. So in order to create, it's actually pretty simple, okay? If you just follow all the calculation here, it's very simple. Because you just need 2 values, right? Just need 2 values. One timer, 2 values, that's it. And they're all 8 bits. So timer's counting, right? Reaches the duty value, pull it down. Keeps counting. Reaches PR2, pull it up. That's it. Pretty straightforward, right? Okay. So in your code, you just need to set up this value and this value to create a certain PWM. That's it. Let me show you another example. This is page 3. Let's start with the data sheet because the data sheet doesn't tell a lie. Okay, so if we start from this formula to calculate PWM period, so let's just write it down first, and then we will transform it to a different version. PRx plus 1 times 4. That's the period. Okay, period OSC times the prescaler value. Okay, let's just use pre here for short. And this one you can convert it because this is PRx plus 1. And this is the frequency, right? So it's a 4 over FOSC and times the prescaler. Okay? And this becomes PRx plus 1 over what? Over FOSC over 4 and divided by the prescaler. And we are very familiar with this because we have been doing this all the time. So in that case, it looks like this is very likely it's the 64 megahertz, the megahertz original clock from the system, the fastest clock you can have. And this divided by this is giving us 16 megahertz. Okay? And that's the prescaler is slowing this down by how many times? So it seems like the timer clock to flip the LSB of the timer 2. It's an 8-bit timer. Okay? It's using FOSC over 4 and then divided by the prescaler to flip the LSB over here. Okay? And that timer, 8-bit timer, is used to compare with PRx or PR2, let's say, PR2. It's also 8-bit or 8 bits. No problem. So it's very clear here. So how did I know that? I verified it using what I have done over here. If we take a look at the MPP settings, it will not be difficult. To save time, I just paused the video, and now I open up MCC and also the MATLAB, and you can see that I set it as 64 microseconds. So this is the same setting as in what you did and what all we did in the in-lab and you should do in the lab. So 64 microseconds, just remember these numbers. I'm going to write it down on the paper. 64 microseconds is 1 to 16 per scalar, okay? This is what we do. And now if we come back to the timer tool, so you do the same setting, you generate it, and it's going to write the values of PR2 is giving you OX3F. I will just write it down. And now let's take a look at it, see if this makes sense, okay? So 3F is basically 63 in decimal, okay? If you use this formula, right? So it becomes 63 plus 1, okay? And now we can directly use whatever we got here, right? Same thing here. We have been doing this all the time. So this is 16 megahertz per second, or 16 megacounts per second, and divided by the prescaler, right? So this is giving us 1 megahertz. It's giving us 1 megahertz, and it's 64 counts. So this is exactly 64 microseconds for the period. So the period register is pre-written a 63 in there, and you plug in the formula, it's going to give you 64 divided by the frequency and also the prescaler's final frequency. So it's giving you this time. We have been doing this all the time. Give the counts, give the frequency, you can find the time. So that's the time to finish that period. And I know this is a good way to verify it because I can look at this one from the oscilloscope. And I was looking at the experiment I did a while ago, and I was able to find some evidence. It's over here. It's over here. Oh, not this one actually. This one. Reduce the duty cycle. So because I use the same setting over here, so I just want to take a look at it. If this period exactly 64 microseconds, so I can verify whatever the calculation, and I'm gonna know that the frequency or the clock being used to count that timer tool, the timer tool's LSB, is going to be that FOC over 4. Okay, let's take a look at it. This is about 40 microseconds per division. So this is 40 microseconds, okay, and this is another 20 microseconds. So this will make a 60 microseconds over here. From here to here will be 60 microseconds. And if you add these a little bit of time over here, so making it very close to 64 microseconds. So we know that this will be true. And if I change the duty cycle, the duty value, right? So it's not changing the period because the period is already written into the PR2 register. It's only changing the duty value here, right? So this is not changing. See? Okay, so this is verified, and now we know that the PR2, according to this one, this is actually true. See, this is true. The timer tool, the 8-bit part of the timer tool. Here, that's the 8-bit timer tool, 8-bit timer tool, and the LSB of this 8-bit timer is using that original frequency divided by 4, which is 60 megahertz. And then divided by the prescaler. Okay, it's important to know this for now. And then for the next one, the diagram looks like this. Okay, you have timer tool, and the datasheet tells you that, since we don't know what the details of the hardware is because it's not showing to us, it's probably patented. And you can see what this is telling us is the 8-bit timer 2 registers concatenated with the 2-bit internal system clock, FOSC, and it seems like it has another 2 bits combining with this 8-bit. So this is 8-bit, this 2-bit. And these 2 bits are toggling and carry out. So the carry out is going to toggle here if it's a 1. Okay, and this LSB is being toggled by FOIC without divided by 4. So if we use the 1-to-1 prescaler, it will be 64 megacounts per second. If you have a prescaler, then divide by prescaler. Okay, no matter what that is, doesn't matter. So this is very interesting, and this is super important to know. Why? Because this timer has two LSBs. Okay, so one LSB over here, which is the real physical LSB, making this one when this one carries out, it's gonna put a carry over here. They are associated with each other, and this LSB being toggled by a 4 times faster clock over here. Okay, it's 4 times faster. Keep in mind. And then if you look at the diagram, we can keep going up. So this one is compared with the PR2 register, which is also 8-bit, and make sure that you know this is aligned to this bit, not this bit. Okay, so which means whenever it's comparing here. Okay, and then you have another, which is a duty value. It's a CCP1L. Okay, and you have 2 more bits, which is a DC1B, 2 bits over here, 2 bits over here, and this one, whenever it needs that duty value, this will be which is basically at the very beginning of the here. Once you finish that PR2 counting, okay, it will do several things. You will send a 1 to it. It will send the duty counts to the CCP1H register. However, keep in mind, if you look at here as well, it's not dropping these 2 bits. It's taking that 2 bits over here to compare with the timer. Keep in mind, okay? So let's draw it. Duplicate it here, DC1B. All right? So the timer, which is the LSB being toggled by this clock, 64 megahertz divided by prescaler, is matching with whatever over here, the 10 bits value over here. Okay, so remember in the code that I have showed you several times, you can always refer back to it if you need over here, right? How the 10 bits are being extracted and put into these 2 registers. Okay, so let's take 255 for example. 255 is giving us 0xFF, which is 11111111. However, the duty value is a 16-bit number. So it has to be A0 is in front of it, right? Like that. That's the real value being stored in the memory in the microcontroller. Okay. So when you are taking out the 10 bits from here, so these 2 bits goes to here, right? So now it's 11, for example, and these 8 bits goes to here, which is 00, and then you have 6 ones. So if you combine them this way, it is still giving you 8 bits. And that 8 bits will be used to match the timer 2 counts starting from this LSB, not here. Keep in mind, from here. So the number doesn't change. The binary number is still 255. Okay? And the frequency now is not this anymore. It's 4 times faster. So this is 64 mega divided by the prescaler. And remember that we have in this example, right? So in whatever we have been using, we have been using 16 as a prescaler. So this is 16. Okay. So this becomes. So if you use 255 divided by 16, and this is giving you. Let's calculate it. 255 actually divided by 4, right? Divided by 4. It's giving you 63.75 microsecond. What does that mean? I mean, this is when it matches this count what does it do? It turns it on, right? Oh no, it turns it off, because it turns on here. When it matches here, it turns it on. And when it matches this number, it turns it off. That's how you define this width over here, which is the duty value, okay? All right. So that means this one takes 63.75 microseconds. However, the remember the original time in PR2? So the period is 64 microseconds. However, if you are writing a 255 into it and you are thinking, hey, I'm giving a 100% duty cycle, it's actually wrong, because it's not 100%. If you use 64 minus 63.75, it's giving you like a quarter microsecond. Okay? And which makes perfect sense, because I just probe it today. So take a look at this. All right? It's 1 microsecond per division, 1 microsecond. It's 1, 2, 3, 4 quarters. So that's exactly 1 quarter of microsecond. That's why if you write a 255 into that EPWM function, you are getting this. All the rest are ones. However, you are missing that 0.25 microsecond. Okay? So now let's come back to the theory, to the math. So my question is, how can you get 100% duty cycle based on what we have learned? You just need to make this one 64 microseconds. And you just need to add 1 to it. Okay? So which changes a lot of things. What has been changed? So in the past, we write a 0xFF to the PWM function. Like whatever, blah, 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 okay? The PWM function. That wouldn't work. You'll see the LED is not 100% off. So if you want to create a 100% duty cycle, you have to use 255 plus 1, which is 0x100. Give this value to that PWM function, you will be able to fully turn it off, and you are getting a more accurate color. Okay? So that's how we do it, and you have to know that for the cube example on the website, right? So you see that color cube. It shows you something like this, right? Whatever, like this, okay? Shows you this. And it shows the origin here is like 255, 255, 255. It's actually not that accurate. It should be 256. It should be 256 instead of 255. Just let you guys know, okay?